For centuries, humanity has dreamed of venturing beyond Earth and exploring the vast cosmos. We have taken our first tentative steps, landing on the moon and sending probes to distant planets. However, one major obstacle remains in our quest for long-duration space travel: the absence of gravity. The human body evolved under the constant influence of Earth's gravity. Prolonged exposure to microgravity leads to a variety of health problems. Artificial gravity, created using rotational motion, offers a potential solution. This technology could revolutionize space travel, enabling us to establish permanent human settlements on other planets. The quest for artificial gravity is no longer confined to science fiction. It is a scientific and engineering challenge that we are actively pursuing. Imagine a future where humans live and work in rotating space habitats. Scientists and engineers are working diligently to design and build the first generation of artificial gravity systems. The journey to create artificial gravity is a testament to human ingenuity and our desire to push the boundaries of what is possible. The principle behind artificial gravity is simple rotation. By spinning a spacecraft, we create a centrifugal force that mimics gravity. This force is proportional to the radius and the square of the angular velocity. Larger structures and faster spins mean stronger artificial gravity. Imagine standing inside a rotating cylinder. The spin pushes you against the inner wall, acting as gravity. Adjusting rotation speed or radius changes the gravity strength. Artificial gravity is a staple of science fiction now becoming reality. The human body is remarkably adaptable, but prolonged exposure to microgravity poses significant health risks. Astronauts on long-duration space missions experience muscle atrophy, bone loss, cardiovascular deconditioning, and immune system dysfunction. These changes can have serious long-term consequences, impacting astronauts' health even after they return to Earth. In the absence of gravity, muscles waste, particularly in the legs and back. Bone density decreases, increasing the risk of fractures. The cardiovascular system adapts to weightlessness, leading to a decrease in blood volume and fluid distribution shifts. The immune system is also affected, making astronauts more susceptible to infections. Artificial gravity offers a promising solution to these health challenges. By providing a simulated gravitational environment, it can help maintain muscle and bone mass, prevent cardiovascular deconditioning, and support immune system function. This would significantly improve astronaut health and safety, paving the way for longer and more ambitious space missions. While large-scale artificial gravity systems are still in development, several promising concepts and prototypes are being explored. These range from rotating space stations and habitats to smaller-scale centrifuges designed to provide short bursts of artificial gravity. One prominent concept involves rotating a spacecraft or habitat to create centrifugal force. This could be achieved by connecting two modules with a tether and spinning them around a common center of mass. Another approach involves building a large rotating torus or cylinder. This design would provide a more stable and uniform gravitational field but requires more complex engineering and construction. Smaller-scale centrifuges offer a more immediate solution for providing short bursts of artificial gravity. Astronauts could spend a portion of each day inside a rotating centrifuge, experiencing a gravitational force similar to that on Earth. These centrifuges could be incorporated into existing spacecraft or future space stations, providing a valuable tool for maintaining astronaut health. Creating artificial gravity in space presents significant engineering challenges. One primary hurdle is the size and scale of the rotating structures required to generate a comfortable gravitational field. Building and launching such large structures into space would be complex and costly. Another challenge is the Coriolis effect, which causes moving objects to deflect from their intended path. The strength of the Coriolis effect depends on the rotation rate of the habitat. Minimizing the Coriolis effect while maintaining sufficient artificial gravity is a delicate balancing act. The materials used to construct rotating habitats must be strong, lightweight, and able to withstand the stresses of long-duration spaceflight. They must also be resistant to radiation and other environmental hazards. The rotating mechanisms themselves must be incredibly reliable and precise. Ensuring the long-term stability and safety of artificial gravity systems is paramount. Living in a rotating environment with artificial gravity would have profound psychological and cultural impacts on astronauts. Adapting to a new sense of down and the Coriolis effect could present initial challenges. astronauts would need to learn how to move and interact with their environment in new ways. The design of habitats with artificial gravity would need to consider the psychological well-being of the inhabitants, creating comfortable and stimulating living spaces. Incorporating natural light and views of Earth or space would be essential for maintaining morale and mental health. The social dynamics within a rotating habitat would also be unique, requiring careful consideration of crew selection and interpersonal relationships. New traditions, customs, and forms of artistic expression might emerge, reflecting the unique experience of life in artificial gravity. The experience of being born and raised in artificial gravity would be fundamentally different from life on Earth. This raises intriguing questions about the long-term effects of artificial gravity on human evolution and development. The Gateway Project, an international lunar outpost planned for the 2020s, represents a significant step towards developing artificial gravity technologies. While the Gateway itself is not designed to have artificial gravity, it serves as a valuable testing ground for many of the technologies and systems essential for future rotating habitats. One key objective of the Gateway project is to demonstrate the feasibility of long-duration space missions beyond low Earth orbit. This includes testing life support systems, advanced propulsion technologies, and other crucial components for future deep space exploration. The lessons learned from the Gateway project will inform the design and construction of future artificial gravity habitats. The Gateway will also serve as a staging point for missions to the lunar surface and beyond. It will provide a platform for scientific research, resource utilization, and the development of new space technologies. The Gateway project represents a collaborative effort between various space agencies and private companies. Artificial gravity becomes even more critical for missions beyond the Moon, such as journeys to Mars and other destinations in deep space. The longer travel times and increased exposure to microgravity on these missions pose significant health risks to astronauts. Artificial gravity would mitigate these risks, enabling healthier and more productive deep space exploration. A rotating spacecraft or habitat could provide a comfortable and safe environment for astronauts during long, interplanetary voyages. The simulated gravity would help maintain their physical and mental well-being, reducing the negative effects of prolonged weightlessness. This would allow astronauts to arrive at their destination in better condition, ready to perform their scientific and exploration duties. The presence of artificial gravity would also simplify many aspects of spacecraft design and operation. Everyday tasks, such as eating, sleeping, and conducting experiments, would be easier and more efficient in a simulated gravity environment. Artificial gravity could also play a crucial role in establishing permanent human settlements on other planets. The concept of artificial gravity has been a staple of science fiction for decades, inspiring generations of scientists and engineers. From the rotating space stations in classic films like 2001, A Space Odyssey, to the elaborate rotating habitats in contemporary science fiction novels, the idea of creating gravity in space has captured our imaginations. Early concepts of artificial gravity often involve massive rotating structures. While these ideas may seem fantastical, they reflect the enduring human fascination with the possibilities of space travel. As our understanding of physics and engineering has advanced, so too have our concepts of artificial gravity. Today, scientists and engineers are working on practical designs for rotating habitats and spacecraft. The transition from science fiction to scientific reality is underway. With continued investment in research and development, we may see the first operational artificial gravity systems within the next few decades. Artificial gravity will transform human history, enabling us to become a spacefaring species. It opens up possibilities for exploration, settlement, and scientific discovery. Imagine humans living and working in rotating habitats on the Moon, Mars, and beyond. Children born in artificial gravity, accustomed to the gentle spin of their world. It will improve health, efficiency, and productivity of space missions, paving the way for longer missions, exploring the solar system and beyond. Artificial gravity is a necessary step for human space exploration. Without it, long-duration space travel and settlement on other planets will remain elusive. Developing artificial gravity is crucial for our future as a spacefaring species. The challenges are significant but not insurmountable. With research and international collaboration, we can create reliable artificial gravity systems. This will pave the way for human expansion into the cosmos. The journey to create artificial gravity is a testament to human ingenuity.